So you need to have the definition for metallic bonding memorized, and they all have the words electrostatic attraction in them. So positive is attracted to negative, for all of them. So for metallic bonds, it's electrostatic attraction. So the attraction between positives and negs, between the lattice of positive ions and delocalized electrons, and the bonding is non-directional. So the electrons just can move around and between them. Okay, so these are all on the left-hand side of the periodic table, and so relatively speaking, their atomic radii are larger and their nucleuses are smaller compared to the right-hand side non-metals, and so those electrons are going to be more free because they're further away and there's less positive in the nucleus, so they're the ones that are going to be more likely to have this sea of electrons. So cations in a sea of electrons is the common definition for it, and that's the reason why they also become cations in the first place, because the electrons are further away from the nucleus. Whereas the non-metals, it's smaller and it's more positive, so they're the ones that end up stealing the electrons. So just one more time, metallic bonds, the electrostatic attraction between a lattice of positive cations and delocalized electrons, and the bonding is non-directional. So just going on just a little bit more detail from there. So how do you know which one's got a stronger metallic bond? So you'll look at the ones, if it's the same size, relatively the same size, the one with the larger charge on it, the larger cation, greater charge, will have a stronger metallic bond. And also, if it's a smaller cation, a little bit like... So if it's a smaller cation, it will have a stronger attraction to the electrons. So ultimately what you want to be is very small and very, very positive, and then you'll have a stronger attraction to the electrons and a stronger metallic bond. So you can see here the majority of elements are metals. If you remember, the magic line is 2 down, 2 down, 2 down, not including aluminium. And so obviously if it's a super large atomic radius, and the distance is far more important than the size, so distance is everything, then these electrons are going to come off super, super easy. So the reactivity is going to increase going down and going this way as well. So going up and going across is going to be a smaller radius and, relatively speaking, smaller distance to the electrons on the outside. So these will be the less reactive ones. So decreased reactivity across the period, decreased reactivity up, or increased reactivity down, however you'd like to say it. Okay, and because they are, the cations here are going to be more closely attracted to the delocalized electrons, the melting point will also increase, and then vice versa decrease. So reactivity and melting point are related in this sense, and there's the explanation there as well. So increased attraction between cations and delocalized electrons, decreasing attraction between cations and delocalized electrons. So that's explaining and describing the melting boiling point and reactivities. This is just to reinforce just one other thing, conduction. So obviously it's those extra particles that are free to move and transfer kinetic energy, and that's the reason why metals are good conductors of heat. And because those electrons can move, it's also why they're good conductors of electricity. And it's just all those little extra ions. So the only other thing that can do that's not metal, is graphite, because the electrons are caught between the sheets and they can move in between those. Okay, they're also malleable, so because they're delocalized electrons, the bonds are non-directional, they're free to move over each other. So the explanation there is close packed layers of positive ions can slide over each other without breaking more bonds than are made. Okay, and that's it for metals.